Yesterday, on July 9th, a swarm of earthquakes began striking underneath the summit of the Pacific Northwest's most potentially dangerous volcano, Mount Rainier. This swarm began at 1:29 a.m. in the morning, with quakes thereafter striking one after the other, sometimes multiple times a minute. This swarm is still ongoing more than 30 hours later, so far involving 221 earthquakes, marking this as the most intense seismic activity Mount Rainier has experienced since 2009, possibly even surpassing the swarm observed in that year. If you are wondering, the reason why these cluster of events are called a swarm is that the earthquakes did not follow the expected rate for a simple aftershock sequence, which is represented here as the best fit 1/x equation. Here's an actual aftershock sequence for comparison. So, should people panic? Absolutely not. As a geologist, as strange as this might sound, I wouldn't even truly consider the ongoing earthquake storm a form of actual volcanic unrest, at least not yet, because I see no evidence of a magmatic component to these events. Supporting my assertion, there's been no volcanic tremor, no increased gas emissions, no change in tiltmeter readings, and no new or existing ground deformation. Every important reading at the volcano is normal, so there's nothing to worry about. In other words, while yes, Mount Rainier is technically an active volcano, at the present it's still essentially sleeping with absolutely zero danger of an eruption in the immediate future, hence the green or normal alert level. On my 0 to 10 opinion-based unrest scale, Rainier's swarm earns it a 0. And yet, these quakes we'd struck could theoretically be considered volcano-tectonic earthquakes, but are not volcanic in the sense that the general public might think of the word. This might sound confusing, but volcano-tectonic earthquakes not only include those directly caused by magma movement, but also from tectonic forces that happen to slightly stress the volcano and the movement of fluids through pre-existing cracks. In the ongoing swarm's case, these events are almost certainly caused by fluid motion, just like Rainier's 2009 swarm. You see, meltwater from the volcano's melting glaciers, general regional precipitation, and groundwater combine and interact with the volcano's hydrothermal system. Due to the deep heat from magma, this can heat the aforementioned water, causing it to rise, and during this process, these fluids may interact with regional faults. This lubricates them, making it easier for them to slip and generate an earthquake. Wherever you go, below ground and sometimes on the surface, active fault lines are fairly common, and this includes at volcanoes, which often utilize larger faults as a path of least resistance for magma to ascend through. It's even been proven that sudden increased meltwater volumes, particularly during the hottest times of the year, such as July, can perform the same process. And once a singular fault slips, other portions of it might as well, and any adjacent faults can also be temporarily activated and slip. It's probably not a coincidence that both strong historical earthquake swarms at Rainier have occurred during the 4 hottest summer months, September in 2009 and July of this year. This is also why earthquakes at many glacier-covered volcanoes, including such as those in Iceland, hence Katla's ongoing swarm, consistently experience increased seismicity in the summer. At Rainier, I have calculated that earthquakes beneath the volcano's summit are 42.8% more common in the warmest 6 months than during the coldest 6 months of the year. All of the ongoing swarm's earthquakes so far have been too small for anyone to feel even right above them, with the largest event being a magnitude 2.1 and the rest being micro-earthquakes, including even negative magnitude earthquakes. Negative magnitude earthquakes can occur as the overall reading system which measures earthquake magnitude is logarithmic, so magnitude 0 has 10 times less of an amplitude than a magnitude 1, and a magnitude -1 has 10 times less of an amplitude than a magnitude 0. While uncommon, this ongoing swarm is still within the normal expected long-term parameters of typical background activity at Mount Rainier. As a final note, I would like to thank my new YouTube channel member Richard Bergen for supporting my work.